Hello everyone. In this video, we are going to take a look at Chapter 7, Section 17.1. Um, First thing first, we're going to briefly study the mass moment of inertia definition. Consider a rigid body with a central mass at g. It is free to rotate about this axis z, and if we apply a torque T about the z-axis to the body begins to rotate with angular velocity, angular acceleration alpha. Both this t, the torque, and the alpha angular acceleration related by this equation t equals I alpha. In this equation, this I is the mass moment of inertia MMI about z-axis. The MMI mass moment of inertia of a body is a property that measures the resistance of body to a angular acceleration. The MMI is often used when analyzing rotational motion. So, in other words, how hard is it to get this thing to rotate? Consider a rigid body and the arbitrary axis P shown in the figure. The MMI about the P axis is defined as I integral dm r squared dm, where r is the moment arm, is the perpendicular distance from the axis to the arbitrary element dm. The mass moment of inertia is always a positive quantity and has a unit of kilogram meter square or slug feet square. These, in this two diagram, thin circular disc and the thin plate, these are the two often most common shapes um, that we see, right? For um, whenever we deal with the three-dimensional bodies here, and then it gives out the formula that we are going to use um, whenever we deal with the thin disk and the thin plate. I want to point it out here is that so thin plate, for example, the first one, a thin plate, for example, depends on where you doing your axis about. If it's about the z axis right here going through right in the middle, I did not want that horizontal line right there. If it's going through the right in the middle, z axis passed through the center of it, so you are going to, the equation is going to be 1/2 mr squared. If your axis is at the edge of the disk, so if it's z prime axis, and it's going to be 3/2 mr squared. And if it's x axis, so this one right here, or y, right, is essentially the same thing. X and y is the same thing. It will be 1/4 of mr squared. Thin plate, similarly, depends on where you're looking at your axis. X, y, and then z depends on where your axis. You're using different equations there. When using direct integration, only symmetric bodies have surface generated by revolving a curve about an axis will be considered here. For shell elements, if a shell element has a weight of z, radius r equals y, and the thickness dy is chosen for integration, then the volume element is dv equals 2 pi r z dy. This element may be used to find the moment of inertia Iz, since the entire element due to its thickness lies at the same perpendicular distance y from the z-axis. For this element, if the disk element having a radius of y and the thickness dz is chosen for integration, then the volume dv will be pi y squared dz. Using the moment of inertia of the disk element, we can integrate to determine the moment of inertia of the entire body. Parallel axis theorem says if the mass moment of inertia of a body about an axis passing through the body's mass center is known, then the moment of inertia about any other parallel axis may be determined by using the parallel axis theorem, which is I equals Ig plus Md. Ig stands for mass moment of inertia about the body's mass center. M is the mass of the body, and d will be the perpendicular distance between the parallel axes. Radius gyration, okay, the mass moment of inertia of a body about a specific axis can be defined using the radius gyration k. Radius gyration has a unit of length and is measured of the distribution of the body's mass about the axis at which the moment of inertia is defined. I equals mk squared, or the other way around, k equals square root of I over n. Composite bodies, if the body is constructed of a number of simple shapes, such as disks, sphere or rod, the mass moment and inertia of the body about an axis can be determined by algebraically adding together all the mass moment of inertia found about the same axis or of the different shapes. Let's take a look at some examples together. We know, given the volume shape shown in the diagram here, we know the rho here, which is density, which is 5 slug per cubic feet. We're looking for the mass moment of inertia of this body about the y-axis right there in the middle. Okay, so based on what we seen, moment in previously given to us, moment and inertia of a disk about an axis perpendicular to this plane will be 1/2 mr squared. If you forgot, let's take a look for your disk and through the middle where I highlighted in red, right through the middle for a disk will be 1/2 mr squared. That's where that comes from. So you have I equals 1/2 mr squared. So for the this element, diy equals 1/2 dmx squared, where the differential mass dm equals rho dv, mass equals density times volume. Okay, that's where that comes from. dm equals rho dv, mass equals density times volume, and you have rho px squared dy, and then you the rest of them are just math. You plug in your integral. Next one, if I have a pendulum consists of the slender rod plus a disc at the bottom. We're looking for, so the rod has a mass of 2 kilogram and the circular plate with a mass of 4 kilogram. We're looking for the pendulum's radius of gyration about an axis perpendicular to the screen and pass through the point O. So passing through the point O, which is the pin support over here, and it's perpendicular to the surface. So center of mass of the rod is at a point GR from point O. Center of mass of the circular plate is at 1 meter. And then 1 meter, so the GP over here is 2.5 meter away from point O. So what it's saying is that we can separate the two pieces. We can separate, look at the rod. Center of mass for this rod is right here, which is 1 meter away from O. And then center of mass for this plate is right here. Okay, so this distance for the rod, this distance right here is 1 meter. And then for the plate, this distance right here is going to be 2 meter plus the 2 meters plus the radius of the plate over here. Radius of plate is 0.5 meter plus the 2 meter, that overall gives me 2.5 meters together. Okay, so that's what it's saying over here. And then using the parallel axis theorem, I have IO equals IG plus MD squared. So starting with the rod, let's take a look at what's going on with the rod. Rod, if you forgot the equation, you can look at it as if it's a thin plate, which is the diagram on the right over here. So you'll have 1/12 and b squared, okay? And it's just a very thin, the b will be very small. So you have 1/2 times the 2, which is the mass, yeah, the mass of the raw 2 kilogram, this one right here. That's what that 2 is, this one, the first 2. And then the second 2 will be how tall that is, so 2 square. And then keep going, you will do md square. Again, mass is 2 kilogram, and then the d will be where we just figure out half of the 2 meters. So multiply by 1 square. That gives you the I for the rod, mmi for the rod. And we're gonna do the same thing for the plate, for the disc. Okay, so for the disc is going to be 1/2 times mass times 0.5, 0.5 being the radius of the disc itself, and then times the md squared. So the 4, 2.5 come out from where we just talked about, from the point O to the center of the disc, which is 2.5 meters total. So plug it in. I have both of them, adding both of them together, adding both of the two MMI together, that gives me that. And then using this equation, if I know the total MMI divided by the mass, 6 kilogram total, I have 2 kilogram for the rod and 4 kilogram for the plate. So together is 6 kilogram. So that taking the square root, that gives me the radius of gyration. All right, next problem. This one is similar to the one that we're looking at. The pendulum consists of 5 kilogram plate and the 3 kilogram rod. We're looking for the radius gyration for the pendulum about an axis perpendicular to the screen and passing through, instead of O, we're passing through G this time. Okay, again, very similar to what we did before. We're gonna calculate the MMI for the plate, for the rod separately, and be careful it's through. So we're calculating where is the center of mass for each one of them. What's the distance between the center of mass and this G right here? Okay, and then adding that two together. I'm gonna skip the explanation here. This one right here will be in the middle, right? And then this one right here will be right here in the middle. All you got to do is figure out how far is it away from the point G, and then the point G, um, we're going to need to figure out where the point G is by using the center of mass of the plate and the rod together. We learned this back in statics. Okay, so sigma y bar m divided by sigma m total. So that gives you, we'll calculate it. It's 1.781. So we're calculating now. The next step will be, well, how far is it away from this 1.781? Now we have the MMI and put them together and divide it by the total mass, and then do a square root that will give me the radius of gyration. Last group problem here. We have a wheel consists of two rings, ring in the middle, small ring outside the big ring, and also we have 8 rods together. We're looking for the mass movement inertia of the wheel about an axis perpendicular string and passing through A. Look, this time we need to pass through A here. Okay, so these we sort of look at it before. So you have, so the mass, we know all of them their mass. The larger ring, the ring outside is 100 pounds. The ring in the middle, smaller ring, is 15 pounds, and then the rod is 20 pounds. So we putting them together, you have the reason we divided by 32.2, right, is because all of them are given to us as weight. We need to convert all of them to mass. That's why you see all of this 100, the 20, the 15, they're all needing to divide 32 divided by 32.2 to give us the actual mass. And then this portion is the rod. We have 8 of them. The rods, we got 8 of them, and it's 112, 1 over 12, and then 20 over 32.2, that's the mass. And the first portion is 3 squared. This is the length square, 3 feet square. And then the second portion is, well, actually, how far are you away from the center? We're doing it from the center because it's a symmetric about the center, and then we're doing it using the parallel axis theorem about point A. So from the center, we know the radius of the ring in the middle is 1 feet. So 1 feet plus half of the length of the rod. The rod total, you got 3 feet, and then half of it will be 1.5. 1.5 plus another 1 feet, which is the radius in the middle, that will give us 2.5. That's where that 2.5 come from. And then we have 8 of them. Okay. And then this one right here, the 15, is the center, the small ring in the middle, and this one right here, because they're all based on the center, right? So this one, the 4 square, 100 divided by 32.2, and then do 4 square is the ring outside, the bigger ring. Putting all of them together, and then we use the parallel axis theorem again. So it will be 89. This is the total, and plus the md square. So the mass total. So this over here, this term. Hold on, let me do it correctly. This term right here inside the parentheses will be the total mass of this entire thing. You have the big ring, small ring, and then 8 of the raw. Divided by 32.2 is the mass. Okay, sorry. This inside the parentheses is the weight of the entire thing. Divided by 32.2 gives me the mass of it. And then we multiply by 4 square, because the distance from O to A is that 1 feet plus the 3 feet. 1 feet is the radius of the smaller ring, and then 3 feet is the length of the rod. So 1 feet plus 3 feet gives me 4 feet. That is 4 feet square. So mr square. So we'll plug that into our equation. That will give us the MMI about point A. Okay, that's all I want to show you in this video. Hope you find this helpful, and thank you for watching.